Hi students, video 4 in our series on partial fractions, and we're going to do some worked examples with what we called case 2, repeated linear factors. And you might recall that for every factor cx plus d all squared in the denominator, we will yield partial fractions of the form b over cx plus d, and also big C over lowercase cx plus d. That's the form, and that's squared, that one. Okay, so we saw our basic form just very quickly from the previous video was when we have something like this. This is in a sort of a basic form that you might see. We haven't got ax or anything like that on the denominator, we've just got x plus c, so not all of them will fit this form exactly, but it's an essential basic form for this. Okay, if you've got that sort of stuff, ax plus b over x plus c all squared. Oh, that's not a squared, that factor is just x plus d. Alright, I overshot my boundary there. Okay, so that will mean that we get following from above, but just a simpler case where the coefficient in front of the x equals 1. We saw this in one of the previous videos. That's your squared, the repeating factor there according to the rule above, and that's uppercase on the numerator. Okay, so that's not new, that's from the previous video. Sometimes we might see it like this. I don't know if you'd call this an extension of case 2. It's not really, but you might see it a little bit like this. These are all very subtle, slight variations on the same case, okay? So, very thinly disguised. But as you can see, it's just all in accordance with the same rule, okay? So just be ready for slight variations on the same theme. Okay, I hope you can appreciate they're all case 2. Let's do 2 worked examples now. So let's resolve 8x plus 10 over x plus 2 all squared into partial fractions, and we have a repeated linear factor there of x plus 2. So in accordance with case 2, this yields partial factors, as you can see on the screen, coming up now. Okay, now once we give them the same, using fraction addition, give them on the right hand side the same denominator, you'll see that we get this. So essentially we can just equate the numerators as we saw in previous videos, and that would mean 8x plus 10 equals a times x plus 2 plus b. And because we're not worried about the denominator now, it is so for any real value of x. So let x equal -2 then, because what we'll have there is that term there will become 0. So that would mean 8 by -2 is -16 plus 10 is -6. -6 equals b, or b equals -6. Okay, so what do we do to find b? There's a couple of ways of thinking it through. You could just look at what we have here, bit of direct reasoning. We have a coefficient times x to the power 1 plus a constant, and we could have that on this side too if we do a bit of expanding. So doing that way looks a bit more explicitly like I was saying. We've got 8x would equate to ax, so very directly a equals 8. Okay, or another way of looking at it is by looking at the constant term 10. So you could say 2a, if you want to be more sure, okay, 2a minus 6 equals 10. 2a is 16, a equals 8, no matter which way you cut and dice it. And voila, we have our partial fractions. Now, how about this in here? It's supposed to have a repeated linear factor, okay? So it doesn't, does it? Maybe it's one of those irreducible quadratics, but you said they weren't going to be happening in this video. You said the video is about something else. Well, look, can it and stop asking me so many questions, okay? We can actually write x squared minus 2x plus 1. Now remembering the identity a squared minus 2ab plus b squared, we do have x minus 1 as a repeated linear factor. Okay, so we just rewrite it and just see if we can reduce that quadratic, and we can. So we have now something that is a case 2, and we keep going then in that vein. So we have 2x plus 10. I've got too many equal signs happening already here. I don't like it. So now that's got to go. Bye. Okay, so we have now got to put out the format for our repeated linear factors there. Case 2, no worries. There we go. So to give those three fraction terms on the right hand side the common denominator so we can equate numerators later on, we've got a, and it's been multiplied by x minus 1 all squared. We have b, which has been multiplied by a factor of x plus 1 and x minus 1. And c, which has been multiplied by x plus 1. Now we can equate the numerator, so it's going to be true for all real numbers. We don't have to worry about dividing by 0. Okay, we got him on the run now. So let's equate these factors here. Now we can eliminate some terms here. If we let x equal 1 to start with, that provides us with 12. Now that will become 0, coefficient with the a, so, and same with the b. So that just leaves the coefficient with the c, so that's 2c, and so c is 6. All right, we can do the same with letting x equal -1. And so we have 8 on the left-hand side, and we have, now be careful with the first term involving a there. We've got -1 minus 1 is -2, but when you square -2, you get +4, so that's 4a. Okay, so always take a bit of care. The term of b is wiped out, and the term of c is wiped out. So in fact, a equals 2. Now, how do we get b is the point of interest there, because we've used up our property, our null properties essentially, that's what I'll call them. and b's got one of each, and we've used both those up. Oh no, what do we do? Well, one thing we can do is we're going to let x equal 0, and it simplifies the left-hand side slightly. So let's have a look at that. So have a look at that. So let x equal 0, so we would have 10. And look, we know a and c already. All right, so we've got, it gives, see, it eliminates the x. The x's are all eliminated once we do this, make x equal 0. So we've just got b as our only unknown because we know a and we know c. Okay, so those parameters are known now. So we've got 0 take 1 all squared is 1. 1 times a, or 1 times 2 is 2. Now b, if we let that term there, x equals 0, if you can see my cursor there, we got 1, and then we got -1. So that's -1 times b, which is minus b. C is equal to 6, and we have 0 substituted in there, so we just have plus 6. Alright, so we have 8 take b equals 10, so b must be negative, and b is -2. So the only slight difference there is that term there. Okay, so that step, I should say. But don't forget, we already know a and c, and if we substitute x equals 0 in there, we knock out that, which does make it very solvable. So using those parameters for a, b, and c, partial fractions are 2 over x plus 1 minus 2 over x minus 1 plus 6, because remember c was equal to 6, 6 over x minus 1 all squared. So there's case 2 examples, partial fractions.